Assalamualaikum warahmatullahi wabarakatuh and good day to all. I'm Azifa Mahyam Zaharuddin. Today I would like to present my paper ID 66 with title A Study on 3D Printing for Cosmetic Packaging on Surface Roughness and Water Absorption Taguchi Method. This is the overview of my presentations. Begin with introductions, followed by methodology, result and discussion, and close with conclusions. The demand for 3D printing in cosmetic packaging has surged due to its versatile application in the modern era. However, achieving good surface quality and high quality of the end product require precise control over the 3D printing process parameter. In 3D printing, a multitude of process parameters dictated the complexity of the printing procedure. These include infill density, infill pattern, printing speed, wheel orientation, K-angle, raster gap, raster size, raster width, layer thickness, nozzle size, filament size, and others. These parameters greatly impact the positions effectively and properties of the final additive manufacturing products. Careful selection of optimization of 3D printing process parameters are crucial for achieving high quality, accuracy, and efficient 3D printing components. Current research lacks a systematic methodology for optimizing the 3D printing process and exploiting the unique features of PLA material specifically for cosmetic packaging. This gap hinders the identification of critical process parameters and their optimal value necessary to attain desired aesthetic qualities and packaging, such as structural integrity and surface finish. Therefore, this research aims to investigate the effect of infill density, infill pattern, and printing speed used in 3D printing for producing a prototype of cosmetic packaging on surface roughness and water absorption. To reduce the waste of printing material when producing cosmetic packaging, Taguchi method was utilized during the experiment to minimize the number of experiments required. The methodology starts with prototype drawing, followed by 3D printing prototype, design of experiment, and finally the testing. The cosmetic packaging design was selected based on an existing product with dimension of 42 mm width and 156.8 mm in overall length, shown in figure. The design was constructed using Autodesk Fusion 360, a computer software program. Following the completion of modeling process within the CAD tool, the model prototype needs to be saved and converted into the SLT file format. This format enables accurate reading by the printing software Ultimate Curer, a slicer software specially designed for the purpose was chosen to convert the model into series of layers and generate the G-code file. This file contains precise instructions tailored to the specific type of 3D printer, facilitating the printing process. PLA was utilized in this study as the filament for 3D printing machine, 3D Espresso. G-code instructions were utilized by the 3D printer to construct the model by sequentially depositing the layers of melting PLA filament according to specified across the layout. Prior to commencing the printing process, it was essential to define and configure parameters such as infill density, infill pattern, and printing speed. Design analysis was performed using the Taguchi method in Minitab statistical software. A total of 9 experiments were designed according to standard Taguchi L9 orthogonal array, which have 9 rows, correspond to the number of tests with 3 factors and 3 levels. Infill density, infill pattern, and the printing speed were selected as the 3D printing parameters to analyze the effect on surface roughness and water absorption. The first column in table was assigned to infill density, second to infill pattern, and finally the third column, printing speed, C. The setting of A include level 1, 3%, level 2, 5%, and level 3, 10%. The second factor was infill pattern, shown in figure. Option of cross, triangle, and trihexagon. Lastly, the third factor explore was the printing speed, C, with level 30 mm per second, level 1, 50 mm per second, level 2, and 100 mm per second, level 3. After the prototype was produced, the prototype will undergo surface roughness testing and water absorption. The surface roughness experiment was conducted using SJ410 Mitutoyo with measurement performed according to ISO 1997 standard. To determine the water absorption percentage, ASTM D570 water uptake was used by immersing the specimen in water for specific duration. However, a modification was made to the standard water absorption test procedure. Instead of fully submerging the prototype in water, water was placed inside the 3D printed prototype, allowing for 24 hours immersion period. To ensure the 3D printing prototypes were free from any pre-existing moisture, the prototype was subjected to 24 hours heating process at 30 degrees Celsius in a specimen dryer prior to the immersion. Water absorption was calculated using the equation given in equation 1, where wet weight is the weight of specimen after immersion and the draining and dry weight is the weight of the specimen after drying. Table shows the experiment result of average surface roughness and water absorption. In this experiment, smaller value of average surface roughness and water absorption were desirable. Set 8, with infill density 10%, triangle infill pattern, and 30 mm per second speed demonstrated the best surface roughness with the average roughness value of 9.203 micrometer. Set 2 with infill density 3%, triangle infill pattern, and 50 mm per second speed show the lowest water absorption value of 2.15%. The analysis of average surface roughness result lead to tables as a ratio for surface roughness, which used to determine the optimal set of parameters from this experimental design. Delta K represents the difference between highest and lowest SN ratio values for each parameters. Larger delta indicate a more significant impact on the outcome of the surface roughness. Infill pattern appear to have the greatest influence on surface roughness, followed by infill density, and finally printing speed. The mean effect plots in figure 3 show the infill pattern has the most significant influence on surface roughness, surpassing the impact of both infill density and printing speed. The mean effect plots confirm that the optimal condition identified align consistently with the information provided in previous table. The control factor infill pattern B at level 3 trihexagonal provide the best result. The optimal value for the SN ratio of smaller the better was obtained through the combinations of 5% infill density, a trihexagon infill pattern, and printing speed of 50 mm per second. These parameters yield the most desirable minimum surface roughness. The data values in table represent the change in water absorption observed when switching between different levels of each factors. Printing speed exhibits the greatest influence on reducing water absorption in 3D printing parts. This is evident from the corresponding delta value 2.257, which is the highest value in the table. Since lower water absorption is generally associated with lower porosity in materials, it can be inferred that the printing speed factor significantly contributes to reducing porosity. The mean effect plots for water absorption show the optimal combinations of level for three control factors from the analysis of water absorption was 5% of infill density, triangle infill pattern, and 100 mm per second of printing speed. In conclusion, Taguchi optimization method effectively utilized to determine the optimal 3D printing parameters for PLA cosmetic packaging. By analyzing surface roughness and water absorption, infill density and infill pattern as critical factor for achieving a smooth surface and low porosity respectively. This study provides valuable insight for cosmetic packaging industry, enable the production of high quality functional PLA packaging with desirable aesthetic and minimal product absorption. Thank you. Assalamualaikum.